If you want to understand the future of global economics, do not look at Silicon Valley.
Right.
And do not look at Wall Street. Look up. Because right now, orbiting above your head, there is a silent multi-trillion-dollar industrial revolution happening in the dark.
It's massive.
It is. I mean, for the last 60 years, we treated space as a museum, a place for flags, footprints, national prestige. But as of 2026, the museum is officially closed. Space is a factory.
Yeah.
Welcome to the Deep Dive. We've got a massive stack of sources today detailing the rise of the off-world economy and what they're calling the AI space cartel. We're going to examine the brutal physics of the the economics of Orbital Foundries, and this multi-trillion-dollar macroeconomic shift that is poised to just entirely crash terrestrial commodity markets.
And, we also need to tease the darker implications of this shift. Because later on, we are going to dive into the weaponization of orbit and a cascading risk scenario that could literally trap humanity on Earth for centuries.
Right, the Kessler stuff. We'll get to that.
Exactly, because this isn't just a conversation about, interesting aerospace hardware. We are analyzing a financial transition that will bankrupt legacy aerospace monopolies and mint the very first off-world trillionaires.
Absolutely. But okay, let's unpack this. Before we can understand why heavy industry is moving to low Earth orbit, we have to look at the physical barrier that kept us trapped down here for over a century. Our sources point heavily to a Russian high school math teacher from 1903 named Konstantin Tsiolkovsky.
Yeah, Tsiolkovsky.
Right. He mapped out the fundamental physics bottleneck of spaceflight, which is the rocket equation.
And that equation has basically acted as the ultimate tyrant over human expansion. It dictates this brutal ratio.
Which is what exactly?
Well, to put just 1 pound of payload into low Earth orbit, you need roughly 20 to 30 pounds of explosive chemical propellant.
Wow.
Yeah. And the insidious nature of this physics problem is that fuel itself has mass. So to lift the fuel that lifts your payload, you're required to add even more fuel just to lift the initial fuel.
It's just an infinite loop of weight.
Exactly. You hit this exponential curve of diminishing returns where the vehicle becomes like 90% volatile chemicals and maybe 10% actual structure and payload.
Right. I was trying to visualize the economic absurdity of this when I was prepping. And the best terrestrial comparison I could find is the commercial airline industry.
Oh, the 747 analogy.
Yeah. Imagine you want to fly a Boeing 747 from New York to London. You build this magnificent, precision-engineered, multi-million-dollar machine. You fly it across the Atlantic, you land it, everyone disembarks, and then the pilot intentionally crashes the 747 into the Thames River, destroying it completely.
Right. Just totally writes it off.
Yeah. And to fly back to New York, the airline has to build a brand new aircraft from scratch.
It sounds insane, but that is the exact economic model the aerospace industry operated under for 50 years with single-use expendable rockets.
That's why.
I mean, you spend $100 million building an orbital launch vehicle, you fire it into the upper atmosphere, it deploys a satellite, and then that massive first-stage booster just falls back into the ocean as flaming debris.
Right.
And that expendable model created a permanent gravity toll booth. For decades, the freight cost to launch a single kilogram of mass into orbit hovered between $20,000 and $50,000.
And at $50,000 a kilogram, you just cannot launch heavy machinery.
No, absolutely not.
You can't launch raw materials or factory components. It is mathematically impossible to run a profitable manufacturing business at those freight rates.
Right. The only assets you can justify putting in space are incredibly lightweight, highly specialized communications satellites funded by, telecom monopolies or scientific instruments subsidized by the bottomless pockets of national governments.
Sure. So what changed? Because the chemistry of propulsion has not fundamentally changed since the 1960s, right?
No, not at all. We still relied on variations of liquid oxygen, highly refined kerosene, and liquid methane. The thermodynamics of combustion are basically identical to the Apollo era.
Right.
The breakthrough that shattered the gravity toll booth was entirely computational.
Let's dig into that computational breakthrough. Because when you watch a booster autonomously navigate back through the atmosphere and land itself backward on a drone ship in the middle of the ocean.
It looks like a hardware miracle.
Exactly. But the sources highlight that this is actually a software triumph. You have a 200-foot tall metal cylinder, which is essentially a flying skyscraper, dropping from the edge of space at hypersonic speeds, hitting chaotic wind shear and changing air density.
And you also have to account for fuel slosh.
Fuel slosh.
Yeah. The residual liquid propellant inside the tanks is violently shifting around during descent, and that alters the vehicle's center of mass by the millisecond.
Oh, wow.
Right? In legacy aerospace engineering, flight computers relied on proportional integral derivative controllers, commonly known as PID loops. These are hard-coded mathematical algorithms designed to correct deviations. So if the rocket tilts 2 degrees left, the PID loop commands a thruster to fire right.
But I'm guessing a rigid PID loop cannot handle the nonlinear, chaotic variables of hypersonic atmospheric reentry.
Exactly. A human pilot cannot react fast enough, and hard-coded logic breaks down when confronted with fluid dynamics inside the tank, fighting unpredictable atmospheric drag outside the tank.
So how do they solve it?
This is where artificial intelligence, specifically reinforcement learning, altered the entire trajectory of the industry. Aerospace engineers basically stopped trying to manually program the rocket on how to land.
Wait, they stopped programming it.
Yeah. Instead, they built hyper-accurate digital twins of the launch vehicles and placed them inside simulated physics environments running on massive server clusters.
So they essentially built a high-fidelity video game and let an AI agent attempt millions of simulated landings per hour.
Precisely. In the simulation, the AI manipulates the titanium grid fins and vectors the engine thrust. It crashes 10 million times. But through brutal, rapid iteration, trial and error, it builds a probabilistic, intuitive model.
I see.
It learns to anticipate the fuel slosh rather than just react to it. It learns how to surf the aerodynamic wind shear.
And when engineers uploaded that trained neural network to the physical flight computers, the success rate stabilized almost immediately.
Right. And suddenly, the most expensive component of the launch architecture, the first stage booster, could fly back, land flawlessly, undergo rapid inspection, get refueled, and fly again days later.
Which completely invalidates my 747 analogy. We're no longer throwing the aircraft into the ocean.
Exactly. And because of this reusability, the marginal cost of a launch has plummeted. The financial data indicates we are dropping from that historical $50,000 a kilogram down to under $100 a kilogram.
And aggressively trending toward $10.
Yes. And when the cost of escaping Earth's gravity drops by 3 orders of magnitude, the fundamental macroeconomic nature of spaceflight shifts. It moves from a bespoke, high-risk expedition business to a high-volume, standardized logistics business.
But here is the immediate economic wall you hit with this new logistics paradigm. With the toll booth suddenly cheap, we aren't just sending up internet mega constellations anymore. We are sending up heavy industry.
Right.
But why go through the immense capital expenditure of building a factory in the vacuum of space when land, water, and labor are so abundant and cheap down here on Earth? I mean, why bother?
Because Earth possesses a massive, invisible manufacturing defect that limits the ceiling of material science.
A defect.
Yeah, that defect is gravity itself. In the realm of advanced materials, gravity is the enemy of perfection. We have to look at a fluid dynamics phenomenon known as buoyancy-driven convection.
Right. I was trying to visualize buoyancy-driven convection from the source notes. It is essentially like a bottle of Italian salad dressing, correct?
That's the perfect analogy, actually.
Right, so you vigorously shake the oil and vinegar together, temporarily mixing them, but the moment you set the bottle on the kitchen counter, gravity rips them apart.
Exactly.
The heavier vinegar sinks to the bottom, and the lighter oil is forced to the top. Earth's gravity is doing that to molten metals and advanced polymers at an atomic level.
Yes. When an industrial foundry on Earth attempts to mix molten alloys to create an aerospace-grade supermetal, or when they try to pull a perfect silicon crystal for an advanced semiconductor, gravity constantly interferes.
It just pulls the heavy stuff down.
Right, it pulls the heavier elemental atoms down and forces the lighter elements up. And as the material cools and solidifies, this microscopic separation creates structural defects, crystalline impurities, and critical weak points.
So the physical weight of the material on Earth is literally crushing its own molecular perfection.
Exactly. But in the sustained microgravity of low Earth orbit, buoyancy-driven convection effectively drops to zero. You can mix materials of vastly different atomic weights like lead and aluminum into perfectly homogeneous alloys that would separate instantly on a terrestrial factory floor.
And the sources highlight one highly lucrative, commercially viable use case that is driving the current capital influx, which is Zblan, spelled Z-B-L-A-N.
Right, the heavy metal fluoride glass.
Yeah. From a theoretical physics standpoint, it is the most efficient fiber-optic transmission material in the universe, possessing an incredibly broad transmission spectrum and astonishingly low signal attenuation.
It is.
But let me push back on that claim for a second.
Right.
Because if this Z-band material is the holy grail of fiber optics, why is the global telecommunications infrastructure not already built with it? Why are data centers still laying standard silica fiber across the ocean floor?
Because it is nearly impossible to manufacture on Earth.
Really?
Yeah. When you melt the precursor chemicals in a terrestrial facility, gravity interferes during the critical cooling phase. As the molten glass transitions to a solid state, the gravitational pull induces microscopic crystallization inside the fiber strand.
And those microscopic crystals act like prisms, right? Scattering the photonic light signals passing through the glass.
Exactly. The fiber becomes opaque, rendering it completely useless for high bandwidth data transmission. But if you extrude that exact same Z-band fiber in the microgravity environment of an autonomous orbital foundry, it cools without interference. It forms a perfectly amorphous, defect-free optical glass.
And the performance metrics are staggering. A single Z-band cable manufactured in orbit could theoretically cross the entire Pacific Ocean without requiring a single signal-boosting repeater station.
Right. Currently, undersea internet cables require incredibly expensive, high-maintenance optical amplifiers every 50 miles just to keep the light signal from fading. Z-band eliminates that infrastructure overhead entirely.
The latency reduction and bandwidth expansion for global telecommunications, military sensing, and algorithmic high-frequency financial trading would be revolutionary.
Oh, totally.
The unit economics of this are fascinating.
Yeah.
The financial models refer to it as mass up, value down.
Yeah, those margins perfectly illustrate why space is the ultimate high-margin industrial zone.
Walk me through it.
Okay, you begin by launching your raw precursor materials. Silica sand and basic fluorides are fundamentally cheap commodities. Let us assume it costs $50,000 in rocket freight to deliver a batch of these raw materials up to your automated commercial space station.
Right, so the mass goes up the gravity well.
Right. Then the AI-managed foundry, operating autonomously in a pressurized microgravity module, pulls the Z-band fiber without human intervention. It transforms a low-value commodity into an ultra-high-value, ultra-low-mass product.
So the value goes down.
Exactly. You load that highly specialized spool of flawless optical fiber into a compact, heat-shielded re-entry capsule and drop it back into the Earth's atmosphere.
Wait. Bringing fragile, hyper-expensive glass back down through the atmosphere sounds like a massive vulnerability in the business model.
It does sound risky, yeah.
I mean, you have a $50 million spool of Z-band,
Yeah.
and you are intentionally dropping it through a 3,000-degree atmospheric plasma field. The insurance premiums on that re-entry alone should destroy the profit margins.
It would have 10 years ago. But the development of miniaturized ablative heat shields and autonomous parafoil recovery systems has made re-entry highly reliable.
Really?
Yeah. The capsule ablates, meaning the outer layer intentionally burns away to dissipate the extreme heat, protecting the insulated payload bay. Then the capsule deploys a guided parafoil and lands gently in a designated desert recovery zone.
Wow.
So that single spool, which required $50,000 in launch freight, hits the terrestrial telecom market valued at $50 million.
A profit margin easily absorbs the launch and recovery overhead.
Completely.
But here is the immediate supply chain wall you hit with these orbital foundries. If you are spending billions of dollars of fiber optics or semiconductor wafers in low Earth orbit, your largest recurring capital expenditure is still dragging the raw material up from Earth.
Right.
To truly detach the space economy from terrestrial inflation and launch bottlenecks, you have to sever the supply chain from the Earth's crust entirely. You have to source the raw material directly from the vacuum.
And this transition from off-world manufacturing to off-world extraction is what the sources categorize as the asteroid arbitrage.
The asteroid arbitrage.
Yeah. And this is where the macroeconomic foundations of the global terrestrial economy begin to fracture.
So we have to examine the terrestrial bottleneck. The modern digital economy, the global transition to renewable energy, and next-generation military hardware all rely on a critically scarce set of elements. Cobalt, lithium, platinum, palladium, and rare earth elements like neodymium and yttrium.
Right.
You cannot manufacture high-density electric vehicle battery a permanent magnet for a wind turbine, or the guidance computer for a hypersonic missile without them.
And mining these elements on Earth is an ecological and geopolitical nightmare.
It really is.
It requires moving millions of tons of topsoil, utilizing highly toxic chemical leaching processes, and operating within concentrated geopolitical monopolies. A single nation currently controls the processing bottleneck for over 80% of the global rare earth supply, granting them immense leverage over global technology markets.
But the sources reveal a fascinating geological reality about why these elements are so rare on the surface in the first place. It is essentially a planetary accident.
Yes, exactly.
When the Earth was first forming billions of years ago and existed as a completely molten sphere of magma, the heaviest elements obeyed gravity.
Right. The vast majority of the planet's iron, gold, platinum, and cobalt physically sank. They were pulled down into the planetary core thousands of miles beneath the mantle, completely inaccessible to any mining technology we will ever possess.
So the only reason we have any accessible veins of precious metals in the Earth's crust today is due to the late heavy bombardment?
Exactly. Millions of years after the crust cooled and solidified, a massive storm of meteorites struck the planet, leaving a superficial dusting of metallic elements on the surface.
That's wild. We are literally destroying terrestrial ecosystems and fighting geopolitical proxy wars to scrape up the crumbs left behind by ancient asteroid impacts.
That's exactly what we're doing. Meanwhile, out in the solar system, the main supply is untouched.
Right.
The sources detail near-Earth asteroids, or NEAs, like Ryugu and Bennu, alongside massive M-type metallic asteroids residing in the main belt, like Psyche.
And these bodies are not simply large boulders of silicate rock, right?
No, many of them are the exposed, highly concentrated metallic cores of shattered protoplanets that failed to form during the birth of the solar system.
The sheer scale of the available resources breaks standard economic models. A single, moderately sized M-type asteroid, roughly 500 meters in diameter, contains more platinum group metals than have been excavated in the entire recorded history of human civilization.
It's just sitting there.
Sitting in the vacuum, entirely unclaimed, representing trillions of dollars of unrefined wealth.
Historically, aerospace engineers and economists dismissed asteroid mining as science fiction.
Sure.
The traditional logic assumed that the capital required to launch a human crew, fly them millions of miles, establish a mining camp, dig up heavy raw rock, and haul it all the way back to Earth would eclipse the market value of the metals.
Right. The economics only work if you remove humans from the equation and utilize in situ resource utilization.
Exactly.
You have to smelt the rock right there in the vacuum. You cannot haul dead weight back to Earth. So how does an autonomous robotic swarm actually catch a tumbling asteroid and process it?
Well, the entire architecture relies heavily on AI optical navigation. As we discussed, latency is a severe operational constraint.
Because of the distance.
Right. You cannot manually pilot a spacecraft via joystick from a control room in Houston when the vehicle is 10 million miles away. The communication signal delay makes real-time control impossible. The mining swarm must be fully autonomous.
So it approaches the target using light detection and ranging, or LiDAR, combined with stereoscopic camera arrays, to render a real-time, high-fidelity, three-dimensional map of the asteroid.
Yes. The AI analyzes the tumbling rotation, identifies the highest surface concentrations of metallic ore, and fires its microthrusters to perfectly match the rotation, gently anchoring the swarm to the surface.
Okay, so it's anchored.
Right. Once anchored, the swarm initiates the ISRU process, because bringing unrefined, useless silicate rock back into the cislunar economy is a massive waste of delta V and propellant.
You only want to move the pure metallic element.
Exactly. And to smelt the ore without a traditional blast furnace, the AI swarm deploys massive solar thermal concentrators.
I picture these as giant, ultra-lightweight parabolic mirrors that unfold like massive origami structures. It is the industrial scale equivalent of a child using a magnifying glass to burn a leaf on a sunny day.
That is exactly the mechanism. In the hard vacuum of space, there is no atmospheric interference to diffuse the solar radiation. These parabolic arrays focus the raw, unfiltered energy of the sun directly onto the surface of the asteroid, generating localized temperatures of several thousand degrees Celsius.
Wow. And the intense thermal shock physically vaporizes the useless silicate rock and captures the volatile gases.
Right.
What remains, cooling in the vacuum, is a highly concentrated, hyper-purified ingot of platinum, cobalt, or neodymium.
And transporting that refined ingot back to the Earth-Moon system does not require a massive, explosive chemical rocket. The AI swarm attaches high-efficiency, low-thrust ion engines directly to the metallic vat.
Because there's zero drag.
Exactly. Because there is zero aerodynamic drag in the vacuum of space, a continuous microscopic push from an ion engine emitting charged xenon gas can accelerate thousands of tons of mass over a period of months. The AI calculates the optimal orbital mechanics to gently spiral this massive block of pure wealth into a stable lunar orbit for collection.
We have to analyze the macroeconomic threat this poses, because the implications are staggering. What happens to the global commodities market when the first commercial asteroid mining conglomerate successfully parks 100 tons of refined platinum and cobalt into lunar orbit, ready for atmospheric re-entry?
The supply curve for these incredibly scarce materials goes vertical.
Terrestrial spot prices will violently crash.
Absolutely. The geopolitical leverage that specific nations currently hold over the rare earth supply chain will evaporate almost overnight. We will essentially enter a localized post-scarcity era for the specific elements required to build advanced technology, batteries, and defense systems.
And the highly leveraged terrestrial mining conglomerates, the companies currently sinking billions of dollars into deep shaft mines and toxic open pit extraction, will be left holding massively devalued stranded assets.
Yeah, they're in trouble.
Their entire market capitalization is predicated on the artificial scarcity of digging miles into the dirt. When an autonomous orbital drone can deliver a pure, refined ingot from the sky at a fraction of the operational cost, terrestrial mining cartels face immediate insolvency.
But this expansive vision introduces a severe logistical bottleneck. We have high-tech orbital foundries spinning flawless fiber optics in low Earth orbit, and we have autonomous swarms smelting precious metals out in deep space.
Right, how do you connect them?
Exactly. How does the off-world economy actually move this massive cargo between these nodes? You cannot launch a dedicated heavy-lift rocket from Florida every single time. You need to move a pallet of processed platinum from the moon to a manufacturing station.
Right. Point-to-point launches from the Earth's surface are a dead end for a mature industrial economy. What the system requires is a localized, fully off-world trucking network. And this brings us to a crucial physics deep dive into the mechanics of orbital logistics. If you look at the history of frontier expansion, whether it is the California Gold Rush or the building of the Transcontinental Railroad, the massive generational wealth is rarely captured by the people panning for gold.
No, it never is. The wealth is captured by the entities selling the pickaxes, the denim jeans, and the rail tickets.
Exactly.
In the space economy, the pickaxes are localized logistics. Specifically, the architecture relies on two critical pieces of infrastructure: the orbital tug and the cryogenic propellant depot.
To understand why a gas station in space is a multi-billion-dollar engineering marvel, we have to explore something called the ullage problem.
Yes, this is fascinating.
The most efficient chemical propellants for moving heavy cargo masses across the solar system are liquid hydrogen and liquid oxygen. But these are cryogenic fluids. They must be maintained at temperatures hundreds of degrees below zero to remain in a liquid state.
And managing thermal dynamics in the vacuum of space is incredibly complex. Space itself does not have a temperature, but objects in space do. A spacecraft orbiting the Earth experiences violent thermal swings. When exposed to direct, unfiltered sunlight, the whole temperature can spike to positive 250 degrees Fahrenheit.
Wow.
And then 45 minutes later, when the spacecraft passes into the shadow of the Earth, the temperature plunges to minus 200 degrees Fahrenheit.
So the cryogenic propellant inside the tanks is constantly fighting to boil off into gas during the sunlight phase and freeze during the shadow phase.
Exactly, but the thermal challenge is actually secondary to the physical behavior of liquids in zero gravity.
How so?
Well, on Earth, if you have a fuel tank, gravity firmly pulls the liquid to the bottom, right where the intake pipe for the engine is located. The gas sits harmlessly at the top.
Makes sense.
But in a state of continuous free fall, or zero gravity, the liquid does not settle. The liquid hydrogen and the gaseous hydrogen mix together, forming a massive, floating, chaotic blob of fluid and bubbles suspended directly in the center of the tank.
And this is the ullage problem.
This is the ullage problem. If a spacecraft attempts to ignite its main engine to move cargo, the turbo pump might accidentally ingest a pocket of empty gas instead of dense liquid fuel,
which instantly cavitates the engine. You are firing an ignition spark into an unstable, starved combustion chamber, effectively blowing the multi-billion-dollar orbital tug into a cloud of shrapnel.
Right. During the Apollo missions, NASA solved this by firing small, secondary solid rocket motors called ullage motors, just to provide a tiny jolt of acceleration. That forced the liquid to the bottom of the tank for a few seconds before igniting the main engine.
But that brute force method is too inefficient and mass intensive for a commercial logistics network, right?
Oh, completely. The modern solution relies entirely on advanced fluid dynamics modeling and AI control systems. Autonomous depots utilize active cryocoolers and AI-managed microthrusters that perfectly calculate the exact continuous fractional thrust required to settle the propellant without wasting reaction mass.
So they have effectively built autonomous stable gas stations in the sky.
Yes.
I want to walk through how a transaction actually works in this new Standard Oil to Vacuum model.
Sure.
Imagine an AI-piloted orbital tug, essentially a reusable spacecraft equipped with standardized robotic manipulator arms. It launches from Earth carrying a bulk shipment of raw silica sand. It rendezvous with a commercial orbital foundry and unloads the cargo.
Okay.
Instead of deorbiting and burning up in the atmosphere, the tug navigates to a cryogenic depot parked in a higher orbit.
Right. The tug autonomously docks with the depot. The AI systems negotiate a secure handshake and manage the highly volatile zero-gravity fluid transfer, pumping liquid oxygen and liquid methane into the tug's depleted tanks.
And fully refueled, the tug undocks, fires its main engines, and initiates a transfer orbit toward the moon to intercept one of those incoming asteroid ingots, towing it back to the foundry.
And the brilliance of this business model is its total detachment from speculative risk.
How so?
The corporation that owns the cryogenic depots and the fleet of orbital tugs does not care if the asteroid mining swarm strikes a vein of pure platinum or a useless chunk of carbon.
Right. They do not care if the Orbital Foundries successfully manufactures flawless glass or goes bankrupt.
Because they collect a toll on every single movement of mass in the cislunar sphere.
Exactly. They sell the propellant at a massive premium, and they charge exorbitant freight rates for the tow. Every corporate satellite, every mining swarm, and every commercial space station inherently relies on that localized logistics network. It is the ultimate monopoly on kinetic movement.
Which transitions us perfectly into the wealth and investment playbook. Because as a listener, you're probably wondering how to actually position yourself for this. The sources explicitly address how retail and institutional investors are trying to allocate capital into this transition and how the vast majority of them are making a fundamental error.
It is a classic retail investor trap.
Yeah.
When the broader public reads headlines about the trillion-dollar space economy, their immediate instinct is to buy equities in the most visible launch providers, or they hunt for high-risk penny stocks attached to speculative asteroid mining startups. But the launch providers are currently locked in a brutal race-to-the-bottom price war.
Right.
If launch costs successfully compress toward $10 a kilogram, the profit margins on the physical rockets will completely evaporate. Launch becomes a commoditized utility like a municipal water line.
Exactly. And asteroid mining, while offering astronomical returns if successful, carries extreme geological and operational risk.
So the contrarian, highly asymmetric investment strategy is to identify and own the critical bottlenecks. You want to invest in the picks and shovels of the AI space cartel.
Yes.
The playbook outlines 4 specific vectors of infrastructure dominance. Let us examine the first vector: space-grade edge compute.
Right. This is critical.
I was reading the technical data on this edge compute bottleneck, and it highlighted a massive vulnerability regarding cosmic radiation. We established earlier that latency prevents us from running complex AI models from a server in Virginia. An orbital tug attempting a hypersonic docking maneuver with a spinning, uncooperative asteroid ingot cannot wait 2.6 seconds for a signal to bounce back and forth from Earth. The artificial intelligence must execute locally, right on the spacecraft's internal hardware. That is edge compute.
But you cannot simply install a commercial off-the-shelf processor into a satellite chassis and expect it to function.
Why not?
Outside the protective magnetic magnetosphere of the Earth, the environment is saturated with ionizing radiation, high-energy cosmic rays, and violent solar flares. If a single high-energy subatomic particle strikes a standard silicon microchip, it can physically alter the electrical charge of a transistor.
Flipping a binary bit from a 0 to a 1.
Exactly. That is called a single event upset. If a cosmic ray flips a bit during a critical docking sequence, the AI navigation model instantly hallucinates. The thrusters misfire, the spacecraft enters an uncontrolled spin, and you destroy $1 billion worth of infrastructure in a microsecond.
Wow. So how do they prevent that?
To survive in the orbital environment, microprocessors must be extensively radiation hardened. This involves utilizing exotic substrate materials like silicon carbide, but more importantly, it requires complex architectural redundancy. The industry standard is triple modular redundancy.
Right, that is where the rad-hard chip actually contains 3 completely separate processors running the exact same mathematical calculations simultaneously. Correct.
Precisely.
If a cosmic ray strikes processor A and flips a bit, causing it to output a faulty navigation command, processors B and C instantly recognize the discrepancy, outvote the damaged processor, and correct the error in milliseconds.
Exactly. The semiconductor foundries that successfully design and manufacture these miniaturized, radiation-hardened, application-specific integrated circuits are the ultimate choke point of the off-world economy. Every autonomous tug, every robotic mining swarm, and every automated factory requires them to function.
The second vector is equally fascinating from a software monopoly perspective. Autonomous docking APIs. This is essentially the TCP/IP protocol of the vacuum.
Right. Consider the foundational architecture of the terrestrial internet. TCP/IP is the universally standardized communication protocol that allows an Apple laptop to seamlessly exchange data with a Microsoft server or a smartphone in Tokyo to stream video from a data center in Brazil.
It is the agreed-upon language of connection.
In space logistics, physical connection is the supreme bottleneck. You cannot deploy an astronaut in an extravehicular pressure suit with a wrench to manually attach a cryogenic fuel line every time a tug needs propellant.
No, obviously not.
The connection must be executed autonomously by machine vision-guided robotic systems. But if an orbital tug manufactured by Company A attempts to dock with a cryogenic depot manufactured by Company B, and their physical docking collars are misaligned, or their machine vision algorithms fail to communicate,
They collide.
they collide. Therefore, the most highly valued software entities in the aerospace sector are the consortiums developing universal space docking APIs. They are establishing the standardized machine vision training models, the telemetry handshake protocols, and the physical grapple fixtures that the entire industry adopts.
They integrate themselves as the absolute standard.
Yes.
And once they establish that standard, they extract a micro royalty every single time 2 corporate spacecraft autonomously dock anywhere in the solar system. It is a brilliant, invisible tax levied on the entire off-world supply chain.
It really is. Now, the third vector addresses a rapidly escalating crisis, space traffic management.
Right.
Low Earth orbit is becoming unsustainably congested. Commercial entities are launching tens of thousands of mega constellation satellites to provide global broadband internet, but hardware fails. Satellites exhaust their station-keeping propellant, their internal electronics succumb to radiation degradation, or the companies simply go bankrupt.
We currently have thousands of dead, uncontrolled chunks of metal and solar panels hurtling around the Earth at 17,000 miles per hour, completely unmonitored.
Exactly.
And there is no international space police force to issue citations.
Regulatory bodies, recognizing the imminent threat, are beginning to implement strict end-of-life disposal mandates for all orbital hardware. A corporation can no longer abandon a derelict satellite in a valuable orbital corridor.
Right.
This regulatory shift creates a massive legally mandated market for AI-driven tow truck satellites.
They are the legally enforced garbage collectors of the new frontier.
Basically, yeah.
If a telecommunications conglomerate loses contact with a satellite, they are legally obligated under threat of massive fines to hire a commercial orbital tow truck. The autonomous vehicle launches, tracks the tumbling debris, grapples it, and fires its engines to drag the dead satellite down into the upper atmosphere where it safely incinerates.
And the companies providing this active debris removal service possess a guaranteed, continually expanding customer base.
Which leads directly to the fourth vector, shorting the legacy players. This represents the contrarian macro hedge strategy. If an investor truly accepts the thesis that off-world extraction and autonomous manufacturing will dominate the next decade, they must analyze who holds the losing hand.
Yeah, we touched on the terrestrial mining conglomerates, the entities burdened with billions of dollars of debt tied to deep shaft rare earth mines.
Their operating margins will be crushed by the influx of pure, vacuum-smelted asteroid commodities.
Exactly. But the legacy aerospace primes, the massive old-school defense contractors, are equally vulnerable.
I say.
For 40 years, the legacy aerospace sector survived on bloated, cost-plus government contracts, meticulously constructing single-use billion-dollar satellite platforms over 10-year development cycles. Their corporate culture is inherently risk-averse and glacially slow.
They just can't keep up.
They simply do not possess the organizational agility to compete with vertically integrated, AI-driven commercial space startups that iterate hardware every 6 months. Executing a calculated short position against these legacy primes acts as a macro hedge against the inevitable rise of the agile off-world economy.
We have outlined the staggering wealth generation, the brilliant engineering solutions, and the strategic positioning required to capitalize on this shift. But the mandate of this show requires us to confront the dark side of this boom.
Yes, we have to talk about the risks.
The source material outlines several catastrophic existential risks associated with the unchecked industrialization of space. The most immediate physical threat is a cascading scenario known as the Kessler syndrome.
Right, and the Kessler syndrome is not speculative science fiction. It is a highly probable kinetic reality derived by NASA astrophysicist Donald Kessler in 1978.
1970.
Yeah. It directly answers the question of what happens when orbital corridors exceed their critical carrying capacity. Space itself is infinitely vast, but the specific, economically viable orbital altitudes we utilize are extremely narrow bands.
And Kessler calculated that if the density of objects in low Earth orbit reaches a specific threshold, a single accidental collision between two derelict satellites would not remain an isolated, manageable event.
Yeah.
It would trigger a hypervelocity fragmentation event.
When two metallic objects collide in orbit at intersecting velocities of over 17,000 miles per hour, the sheer kinetic energy instantly vaporizes the impact zones and shatters the remaining structures into thousands of pieces of jagged debris.
Oh, wow.
Each individual fragment of shrapnel continues orbiting at 17,000 miles per hour. They effectively become untrackable hypersonic bullets.
And those thousands of hypersonic bullets inevitably cross paths with other functioning satellites.
Exactly. It triggers an exponential cascading chain reaction. The initial collision destroys two satellites, generating 10,000 fragments. Those fragments strike 50 more satellites, generating 1 million fragments, which then systematically shred every other piece of hardware operating in that orbital shell.
That's terrifying.
The entire environment is reduced to a chaotic, lethal blender of high-speed shrapnel.
The economic and societal implications of a full Kessler cascade are apocalyptic. The off-world economy dies instantly, but the terrestrial impact is catastrophic.
Oh, completely.
The global GPS network, which synchronizes the timing of the international banking system, fails. Global telecommunications and logistics tracking fail. Advanced weather forecasting and early warning military surveillance systems are blinded. We would be violently thrust back into a 1970s technological paradigm overnight.
Furthermore, the Earth would be physically encased within a lethal, swirling cage of microscopic shrapnel. Because the debris is traveling at such immense velocities, even a fragment the size of a paint fleck possesses the kinetic energy to puncture a pressurized spacecraft hull.
So no one could leave.
No human crew or commercial rocket could safely launch through that debris field. Humanity would be physically trapped on Earth, locked behind a cage of our own manufactured garbage, for centuries until the fragment's orbits naturally decayed into the atmosphere.
It is the ultimate manifestation of the tragedy of the commons. Our sources highlight a critical flaw in international law. There is no central global authority regulating commercial space traffic or enforcing safe distances. The financial incentives driving the AI space cartel encourage launching as many foundries, depots, and satellites as quickly and cheaply as possible to establish insurmountable market dominance. Every individual corporation benefits financially from launching more hardware, but by doing so, they collectively externalize the risk of a cascading collision onto the entire planet. They are playing a multi-trillion-dollar game of orbital chicken.
And that physical risk is compounded by the severe geopolitical instability of the current transition. We are rapidly moving from a unipolar domain, largely dominated by the United States and its allies since the end of the Cold War, into a highly contested multipolar arena.
Right.
And the most highly sought-after real estate in the solar system right now is not a platinum-rich asteroid, it is the South Pole of the Moon.
The South Pole.
Yes, the lunar South Pole contains deep, permanently shadowed craters that have not seen sunlight in billions of years. These craters act as massive cold traps, harboring millions of tons of ancient water ice. And the strategic value of water ice is not for human hydration. It is the fact that water, when subjected to solar-powered electrolysis, can be cleanly split into its constituent elements, liquid hydrogen and liquid oxygen.
Which is the exact cryogenic propellant required to fuel the orbital trucking network.
Exactly. The sovereign nation or commercial entity that successfully establishes a permanent extraction facility at the lunar South Pole effectively controls the primary low-gravity gas station for the entire cislunar economy.
Wow.
We are already witnessing international space agencies and state-backed corporations aggressively declaring safety exclusion zones around their planned lunar landing sites. They are quietly carving out sovereign, exclusive territory, directly subverting the foundational principles of the 1967 Outer Space Treaty.
This brings us to a chilling realization regarding the underlying technology of the off-world economy. We spent the last hour praising the brilliant engineering of AI-piloted orbital tugs. We marveled at how they utilize advanced optical navigation and delicate robotic manipulator arms to autonomously dock with fuel depots or gently tow massive asteroid ingots.
Right.
But this is fundamentally inherently dual-use technology.
It is. It is the terrifying reality of the orbital domain. An autonomous tug designed to approach, grapple, and refuel a commercial communication satellite possesses the exact hardware and software architecture required to approach a rival nation's billion-dollar early warning spy satellite.
Right.
With a simple encrypted software update from the ground, that peaceful logistics tug can silently approach the military asset, extend its robotic arms, and violently snap the solar panels off, blinding the adversary.
I was reading an interview with the founder of one of these satellite servicing startups, and the human element of this realization was incredibly dark. He spent a decade building an elegant, peaceful machine designed to clean up orbital debris and refuel dying satellites.
Yeah.
And he was certainly approached by defense contractors who made it explicitly clear that his life's work was the most efficient orbital weapon ever designed. The infrastructure of the commercial space cartel is inextricably fused to the military-industrial complex.
Space is no longer a peaceful sanctuary for scientific pursuit. It represents the ultimate military high ground. The highly advanced autonomous navigation algorithms utilized to hunt and capture tumbling asteroids are mathematically identical to the algorithms required to guide orbital interceptor missiles and hypersonic glide vehicles.
All the same tech.
Exactly. If geopolitical tensions on Earth ever fracture into open conflict, the first battles of the next global war will not resemble a cinematic science fiction movie with human fighter pilots and laser blasts.
It will be fought by autonomous, highly classified machines, ruthlessly and systematically dismantling, blinding, and destroying each other's critical infrastructure in the freezing dark, in total silence.
Yes.
And the civilian population down here on the ground will likely remain completely unaware that the war has even commenced until the moment their smartphone navigation screens go blank, their financial transactions fail to clear, and they look up and realize, we have lost the sky.
It is a fragile, hyper-complex system operating on the absolute edge of human capability and international law.
It really is. Let us synthesize the core takeaways from today's deep dive, because we have covered a staggering amount of data, physics, and macroeconomic theory.
We definitely have.
First, the physical gravity wall is no longer an insurmountable economic barrier. The convergence of reusable launch vehicle hardware and AI reinforcement learning software has permanently shattered the financial grip of the Tsiolkovsky rocket equation. Second, as freight costs plummet toward $10 a kilogram, heavy industry is migrating to low Earth orbit. Orbital Foundries are explicitly exploiting the microgravity environment to bypass buoyancy-driven convection, manufacturing flawless ultra-high margin materials like Zipline fiber optics, completely breaking the physical limitations of terrestrial manufacturing.
Right.
Third, autonomous AI swarm robotics utilizing solar thermal concentrators and ion propulsion are actively targeting near-Earth asteroids. They intend to extract and refine pure rare earth metals and platinum group elements, introducing a sudden, massive supply shock that poses an existential threat to heavily leveraged terrestrial mining cartels and geopolitical resource monopolies.
And finally, the foundational, most reliable wealth generation within this new frontier will not stem from the speculative asteroid materials or the commoditized launch vehicles themselves. The true, enduring monopolies will be established within the localized logistics layer. The corporations controlling the radiation-hardened edge compute hardware, the standardized autonomous docking APIs, and the cryogenic orbital fuel depots that every other off-world enterprise requires to function. However, this unchecked, aggressive industrial expansion flirts daily with the catastrophic kinetic risk of the Kessler syndrome and the silent, rapid weaponization of orbital infrastructure.
It's a massive, incredibly precarious balancing act, and I want to turn this directly to you, the listener, with a final, massive philosophical and legal question to chew on, derived straight from the source material we analyze today.
It is the specific debate that will dictate the foundation of space law for the next century.
If an autonomous AI-guided robotic drone flies millions of miles into the solar system, autonomously smelts a single metallic asteroid, and returns to Earth orbit with an ingot of refined platinum and cobalt, possessing more cumulative wealth than the entire Earth has ever generated in the history of human civilization, should that astronomical wealth belong exclusively to the private corporation that financed the software and captured the rock? Or is the untouched, pristine wealth of the broader solar system fundamentally the common heritage of all humanity? Who legally owns the future?
We do not currently possess a legal framework capable of answering that question, but the market is moving faster than the legislation, and we will need an answer very soon.
It is an absolutely fascinating paradigm shift. Listen, if this deep dive provided you with a new, data-driven perspective on the mechanics and the brutal economics of the off-world economy, drop your thoughts on that final question in the comments below. Stay curious and stay strategically positioned. Continue to educate yourself as this industrial revolution quietly unfolds above us. And I must explicitly remind you that everything we discussed today is educational commentary based on our analysis of the source material. It is not financial or investment advice. Always do your own rigorous research before deploying capital into any market.
The technological landscape is shifting far too rapidly to rely on outdated assumptions.
It truly is. So the next time you step outside and look up at the clear night sky, do not look for the untouchable museum. Do not look for the romantic domain of the gods. Look for the massive multi-trillion-dollar construction site. Look for the industrial zone, because it is up there and the foundations are being built right now. Thanks for joining us.